Hello, my name's Glyn Bird, and today's presentation is called Go Fast and Don't Slow Down. You should see my contact details there. We're going to be talking about my database journey, the databases I've used in my career so far and where it got me, and the differences between operational and analytic data stores. And we'll be pairing off SQL and NoSQL databases, not competitively, but just to look at the advantages and disadvantages of each, and then we will be looking at whether we can use both together. So let's get started. So developers love greenfield projects. They like to be able to start from scratch, rebuild an existing system in the way that it's built today, because when systems develop over time, they pick up cruft on the way. They pick up features that were added but were never needed again. The data design may not reflect, the data design at the start of the project may not reflect the way it is today, and a rewrite would really allow you to clean out the project and build it in a lean fashion, using the latest technology, the latest tools, the latest programming languages and frameworks. So the conversation with your boss would go something like this. I'd like to take 6 to 9 months to rewrite our perfectly working IT system from scratch. And your boss would say, not so much. It's not often in an IT career that you get the privilege of being able to rewrite an existing system from scratch, because for these very reasons. But in my career, I have had that opportunity of rewriting an existing system completely. And it's usually coincided with a change of data store. And if you're using a system for long enough, you'll find that you have to do this because things go out of date and you need to replace stuff. So let's see what my database journey looks like. So when I started doing computers back in the day, there was no such thing as a database. It was just files, and you could store data on a file system in any format you like and retrieve it. And because the file system was local, it was relatively fast. But then along came the web, and we needed to employ a database to handle concurrent access to the same data. And there you go. We chose MySQL. Why? Because it came with the operating system, really. It came packaged in Linux. It came with PHP and Apache HTTPD in a stack, the LAMP stack, and everything worked together well. There was no other software installations required. If we wanted to swap out MySQL for Postgres, we would have had to go to extra efforts. And oftentimes, the choice of software stack comes from expedience rather than experience. So this served me well, actually. I use MySQL in a LAMP stack to power the application we're going to talk about for many years, and it worked fine. But then about 10 years in, there came a fork in the road. Should I swap out MySQL for a more grown-up database like Postgres? Or should I take a right turn and pick a different choice of database, a whole different paradigm, really? And we chose that path. We went with CouchDB, which is a NoSQL database, which we'll talk about in a minute. And along the way, there were other data stores as well. So you can go deep into the woods and get lost in those. But all of these databases are perfectly good. They all have their own strengths and weaknesses. And if you use them right, and you use them for in the way that they were intended, you can get good results. So what was this application? It was a business directory. You'll know the sort of thing. So you go to a website, and they have a database of businesses, and you search for, let's say, Indian restaurants in London, and it returns you a list of listings, potential search results, and then you narrow that search set down by some of the features. Does it have disabled access? Does it allow? Is it pet friendly or whatever? And then you get down to the one that you want, and you click on it, and you'll see all of the details about that business, whether it be photos and videos and reviews and all the other pieces of data that they have. And we serve this business directory out on various platforms, on various brands, web-based and app-based, and through an API as well. So we had 3 to 4 million UK businesses at the time, and that data was changing monthly from incoming data sources, and it was being changed by the business owners themselves that could claim their listings, and they could amend the details, adding color to the information that we had from the stock data we were getting. And we were serving out millions of search results and page views per day or per week. So the sort of schema we were using, this is on a MySQL database, there was a central table called company or companies, I can't remember. And this is the core data store, and it stores one row per company with the company ID, the company name, the address details, which category it belongs to, and so on. But as the application developed, and as we added more features, we found that we needed more tables. So we were adding sort of satellite tables, each one servicing a one-to-many relationship. So a company has many tags, a company has many locations. And we ended up moving things out of the core company table, like which category is it in, into a sort of separate categories table, so we could have a one-to-many relationship. A company could have many categories. And these satellite tables proliferated. We had many of them as we kept adding features and being able to add more extra objects that were attached to this company record. We had more and more of these tables. And the problem we had with this is that if we wanted to pull back everything we knew about that single company or a single company, we didn't have to just contact the company table. We had to resolve the joins and end up doing 10 or 20 queries to pull back everything we know about one company. And as this was a very common use case, it became quite an expensive thing, and we were getting slightly concerned about it. So why did we switch from SQL to NoSQL? Well, it came down to 4 things. The first one we've already met, the number of tables. And this was a problem, as I've explained, about getting all of the details about one business, which was a common use case, was relatively tricky. The second thing was the fear of migration. I don't know if this means anything to you, but if we ever wanted to add a column to an existing database, table, or change one of the indexed fields, or perform some other operation on the database, then one of us developers would have to stay back after hours, wait till the traffic dropped to a reasonable level, switch off one of the master servers, direct the traffic to the other master server, and then apply the patch, wait for it to build, and then do the same thing to the other server, all to avoid there being any downtime or any slowness in the system. Because if we just threw this migration into the database, we could end up with 30 minutes of downtime or 30 minutes of really slow performance. And the business just would not tolerate any downtime. So we began to fear these migrations. They would be done on a weekend on a deadline. And if it went wrong, you were in trouble because you couldn't get back from it. So we hated these migrations and would do anything to avoid them if we could, which isn't a great way to get good practice. You're in fear of the technology that you're using. It's not a good place to be. The other thing was scalability. So the business was saying, well, the 3 to 4 million rows that you've got in your database, in your company's table, is about to grow. We're going to do deals with US suppliers of data and Australian suppliers of data and Indian suppliers of data. I mean, we could end up with a much bigger data set, 20 million, 100 million rows. Can this system cope with it? Have you engineered this system to scale massively? And we weren't sure, actually. We weren't sure that the existing system would be able to cope with it, especially when it's not just a data size problem, it's a usage problem too. the number of queries would increase, the traffic would increase, and we'd have to service it all in the same time. And the fear of the migration piece comes back to haunt us again. If you're then migrating a table that has 100 million things in it instead of 3 million things in it, the time for the migration increases. So, and on top of all of this was the migration to a cloud-based service. That is not just saying hardware is migrated to the cloud. That was underway anyway, but also avoiding managing our own services. We wanted to auto-scale things if possible, and we knew pretty well how to auto-scale the kind of front-end application. That's the easy bit. The scaling a stateless front-end is very straightforward. You just spin up n servers and put a load balancer in front of it, and if one dies, it reboots and comes back again. Scaling a stateful service like a database is much harder to do. So we wanted to outsource that part and find a database provider who would manage that whole service, and they could be up in the middle of the night changing disks and patching operating systems. We could get on with the core competency that we had, which was building business directories. So what does data look like in a NoSQL world? So we chose a JSON document store. So instead of storing rows and columns and normalized data sets, you end up with a single collection storing your company data, where each item is a JSON object, and each one represents everything you know about that company in one place. So this is the same. This represents not only the data coming from the company's table, but all the satellite tables too. So the contacts, the photos, locations, and so on are all arrays of sub-objects. So this one object includes everything we need to know about that company, and it's all added and modified together atomically. So, and it also means it's very easy for us to pull back everything we know about that company. It's no longer inquiring about 20 different tables and joining all the data together. We just go to this one collection and say, get me the data for this ID, please. And it's a single key value store lookup. So there was a choice of technologies. We could use a number of products. We ended up choosing Apache CouchDB. If you're not familiar with it, I'll just spend a couple of minutes describing what it does. It's an open source project. It's part of the Apache Foundation, and it stores JSON documents in collections called databases. So a CouchDB database is equivalent to a Postgres table, a collection of things that are related. It has an HTTP API, so there's no special drivers, there's no special protocol that your application needs to speak between you and the database. It's just HTTP. So anything that can speak HTTP can talk to the database, a mobile application, your command line tools, browser, anything. It has many secondary indexing capabilities, all of which are slightly different and are probably beyond the scope of this discussion. But it crucially it had some search tools, so we could do our sort of free text search that we needed to be able to do our Indian restaurants in London type of problem. So it was not only the core store of data, but it could also be the search technology. It's open source and it's written in Erlang, which you don't particularly need to know to be able to use it. But crucially, it was run as a service by a company called Cloudant. Cloudant was a startup. It was later acquired by IBM, and IBM still runs Cloudant as a service, which is basically CouchDB as a service. And that's the part of IBM I work at today. Now, one of the features of CouchDB is its replication. So once you've set up a Cloudant database, let's say in the US, you can replicate that data to Europe, and the two can be connected in both directions, both syncing each other's changes. So you end up with two transatlantic data stores that are replicating with each other, feeding off each other's changes. And we'll come back to why that's important later. But it allows you to create any complex topology you want. to spread the load around the globe, or to have local on-site stores syncing to cloud-based stores, anything you want. So that's bear that in mind, because we're going to talk about that later. So did it solve our problems, our main anxieties that we had with our SQL service? The answer is mainly yes. We did get rid of the table bloat. We only ended up with one core companies collection, if you like, with bigger, fatter objects representing one business. So that's good. The scalability was solved because CouchDB is a distributed database where you just add more nodes if you want more data, or you want to be able to deal with more traffic, which was great. So we knew we could just pay the service provider more money if we wanted a bigger database, or we wanted more users to use it, which is great. And it ticked the cloud box because it was run as a service. So we didn't need to worry about it. We didn't need to get up in the middle of the night to change disks or patch operating systems. The one thing it didn't quite live up to expectations is the fear of the migration. There was still a little bit of a fear of a migration, because although CouchDB is a schemaless database, you don't need to tell the database the form of the JSON you're storing before you store it, which might seem odd to a Postgres audience. You just throw in a JSON object of any form, and the second object you throw in needn't be the same form as the first. The database doesn't care. It's just going to store the JSON data in its database and return it to you when you want it back. But if you want to search for things, if you want to create secondary indexes, then you do need to be careful about migrations, because if you change a secondary index, then that index will rebuild, and that has a time. It'll take a time to spool through the millions of records and so on. So there was a fear of migration, but only in terms of secondary indexes. So we solved part of that problem. It wasn't as bad as with a SQL database, we found. But there was another factor that we didn't anticipate missing, and that was the SQL itself. Not the language per se, but the ability to query our data in any way we saw fit. So once you put your data into CouchDB, you can set up secondary indexes to perform the main use cases that your application needs: searching by category, searching by keywords, filtering by this, that, and the other. But if your business is coming to you and saying, hey, we'd like to find out how many customers signed up yesterday, we would say, okay, well, we're going to have to create an index that can answer that question. We can't just do ad hoc SQL on the data. And if we did create that index to answer the question, by the time we'd done it, there'd be a follow-up question like, well, how many of those had Facebook profiles? And well, how does that compare to this time last week? And what about that plotted on a map? And so on. So in other words, the business's reporting questions were outstripping our ability to answer them using CouchDB as the database. And we realized we didn't really want our frontline operational data store to be answering business intelligence questions, because they were ad hoc in nature, they were exploratory and iterative, they would change on a daily basis, and they had an unknown effect on performance. They could effectively slow down the frontline operation of serving out what-where queries to our customers. So this led us to the notion of operational data stores versus data warehouses. And we can define the terms here in the terms of this application. An operational data store's main use case is to be always on. It's got to be always up, because my business cannot tolerate any downtime. So it's got to be highly available. It's got to be durable. I don't want to lose any data. So CouchDB stores data in triplicate, so that's good. It's got to be scalable. We've already talked about scalability, just adding more nodes to the database, that's good. And it's got to power our live service. And in that sense, it's really quite a conservative system. It has a number of fixed indexes whose job it is to do one thing for our front-end service. We don't want too many indexes because each index will add an extra load on the system to calculate as the data changes. So we only want to index the fields we need. Now, for a data warehouse, almost the opposite is true. We don't really care. It can be up and down. It's probably got a fixed capacity. It's got ad hoc queries. We can index different fields to the ones we need for the operational use cases. And in some cases, all the fields are indexed by storing them in a sort of column-oriented format, as some data warehouses do. So it's an almost completely different system. So the question is, can we do both? Is there a magic bullet system where you can have your operational data store servicing your frontline application and powering your ad hoc queries coming from the business to power business intelligence and reports? And the conclusion we came to was, no, there isn't a silver bullet to this. You probably want two separate systems, even if it turns out to be Postgres at the front line and Postgres in the back office. You can solve this problem by having a read replica that you hit for ad hoc queries that is separate to the front end. The key point here is that we want to ensure that they are isolated from each other so that any expensive query you do on the data warehouse doesn't affect the performance of your frontline systems. So this is what we came up with. We came up with a system whereby our Cloudant database, which is powering our front-end search services and is our operational data store, has a changes feed, which is usually used to power replication to another Cloudant database. So we intercept the changes feed, which is an HTTP stream of all the inserts, updates, and delete operations for all of the JSON objects in the database. And we turn those JSON objects into SQL, which is written to a SQL relational database. Now, one JSON object might be broken into multiple SQL statements. In other words, we might break out our categories, tags, videos, reviews, and whatever, the one-to-manys back into separate tables for the SQL database, but keep them as objects in our front-end database. So we end up with a sort of best of both worlds approach, where we can pull back everything we want to know about a business as an object from the front-end system, but it's all broken out into separate tables for our back-end system. So this was entirely custom code written for our one purpose for this particular application. And that code was closed source and belongs to my previous employer. I presume it's still in operation, I don't know. But since then, I've written something more generic. It's called couchwarehouse. It's a command line utility and it's open source. And if you point couchwarehouse to your CouchDB database, which is just a URL because it's got an HTTP API, and you tell it which database to use and which database type you want to write to, in this case Postgres, then it will stream the changes feed from CouchDB and write the data to Postgres, giving you a data warehouse. So let's share my screen and I will show you how it works. Bear with me. So hopefully on the screen here you will see a login to CouchDB page. So this is the CouchDB dashboard. So as I said to you before, it's got an HTTP API, so there's not really much to see with a CouchDB database, but it does have a web-based admin panel, so I can log in here to see my databases. And this itself is just an HTTP API client. You can see here there's a list of databases. I've got one called People, and it's 11 megabytes. It's got 20,000 documents in it, and some others. If I click into People, I should see the documents. So a document has an ID, that's the unique identifier, and any number of fields that you can add. As I say, it's schemaless, so you can add as many keys as you want, and the object can be as complicated as you want. I've kept it relatively simple for this demo. So here is a person object, so these are people. So there's an ID, which is just a jumble of letters. this is the first name and last name, date of birth, a sub-object with an address in it, a sub-object with the location in it, and so on, and any fields you like. So this represents one person, and we've got 20,000 of them. So let's flip to the command line here. So I've got 3 tabs on this terminal. On this tab, I'm going to use my couchwarehouse tool to start spooling the data. So if I issue the command couchwarehouse on the database people that we've just seen, and I want to write my data to a Postgres database, if I press enter here, it should start reading the changes feed from that CouchDB database, which is running locally, so it should be nice and fast. And it's giving me instructions here on how to query this once it's done. So it's finished all the changes. So if I pop into Postgres, I should be able to see that data. So in this other tab with the blue background, this is going to be my Postgres terminal. So if I go into pSQL here, I'll just get my cheat sheet on the other side. So I should be able to say, I should now have a table called people that's been created for me by CouchWarehouse. And if I do select count star from people, I've got 20,000 things. So it matches the total I saw on CouchDB. And of course, I can just do any queries I like. Select star from people, limit 5, and I see a list of the people. And you can see the fields, first name, date of birth. These sub-objects, like address, which was an object, is turned into address underscore street, address underscore city. So that is the street attribute was inside an address object, but all the data is there. Because this is a data warehouse, I can do more complicated queries, things that I might not be able to do very easily in CouchDB. In other words, find me all of the people by state and count them, and then order them by frequency and so on. So that's pretty straightforward. I didn't have to do anything. I didn't have to tell it the schema beforehand. It worked out the fields. It created the right data types on the target database for me. And one interesting thing here is that if I go back to my CouchDB end and I pick this person here, Austin Richmond, now he's got the wrong address. I think Nashua is in New Hampshire, isn't it? I'm going to change it to New Hampshire, and we'll call him Austin Smith. I'll just make a note of his ID field, and I press save here. So I've saved the document into CouchDB. That should have gone through the changes feed, and because my Couch Warehouse is still running here, and it's still monitoring the changes feed, that change should have made it through to Postgres. So if I select star from people, where the ID is that person's ID, I should see it says Austin Smith, Nashua, New Hampshire. And so it's picked up the change, and it's kept my data warehouse in sync with my front-end data store. So in this application, CouchDB is handling my operational queries, and this Postgres is handling my data warehouse iterative ad hoc query service. So let's just give it a bit more to deal with. So in this third window here, I'm just about to create some more data. So we had 20,000 records in there. So if I want to, I've got a sort of template file here called person.json. So this is just a sort of template person, and these little placeholders are going to get filled out with pretend data. So if I've got a utility called data maker, and if I pass it that template, it's going to fill out the data with some realistic-ish data. It's not very good at place names. But if I use that in bulk and I create 5,000 new records, so I'm taking my person template, passing it to data maker, saying I want 5,000 of them, and I'm passing it to this other utility called couch import to import that data. It's now writing 5,000 records to CouchDB, and by the time I get to Postgres here, and I say select count star from people, I've got 25,000 documents. And if I just one final demo, if I just delete a person here, so that I should have 24,999 people. So this is staying perfectly in sync. I don't have to keep it that way. So this is only staying in sync because my couch warehouse utility is still running. If I stopped it, then the front end would continue, the data would continue to change, and the back end data would remain static. And if that's the way you want it to run, then that's fine. And I can see the appeal of that, because you could run this couch warehouse utility overnight, say, and it would catch up with today's changes, and then just leave it static so that the view of the data that you're using for reporting remains static throughout the working day, and then a cron job running at nighttime continues the couch warehouse process from where it left off last time. Because if I stop it and restart it, it will just carry on from where it left off. It won't spool all the changes from zero again. So let's head back to the slides. I'll stop the screen share. And we will proceed with the conclusions. So what we've talked about today really is the difference between operational and data warehouse stores, and keeping the two separate so that the front end can continue to be performant and scale nicely, while the business still gets the back end data exploration benefits of being able to ask any query of their data at any time without affecting the performance of the front end. And it's all about picking the right tool for the job. If there's one thing you take away from this, it's be good at data movement. Don't be afraid of taking data from one system and putting it in another. Don't necessarily try to get every use case out of your one data store, which is sometimes a temptation, especially if you're paying for it, is to wring the last ounce of value out of the asset that you've paid for. But just, if there's a better data store for the job that you're trying to do, then just get good at data movement. Get the data out of where it is at the moment and put it somewhere else, and keep the two in sync if you can. So the question you ask your boss shouldn't be, can I rewrite the system with the latest technology and the newest thing? It might be, I'd like to take a live copy of our primary data and put it into a data warehouse. And you might get a more positive reaction than you're fired. So thank you very much for listening. My name's Glyn Bird, and if you have any questions, please let me know. Thank you very much. Hi, Josh, can you hear me? Sure. How is it easy to create an app using CouchDB to modify a field value? So the way that this is working is that the Couch Warehouse tool is listening to the changes feed coming from CouchDB, and that can either be effectively an insert operation, an update to an existing record, or a deletion, and that we transform that into SQL at the target end, on the data warehouse end. And it's relatively easy to keep things in sync, unless there's a big caveat here, unless your schema changes. So I said in the presentation that the CouchDB side is schemaless. You can vary the schema easily. You can just add another field. You can add a different thing to your address. You can change, add a second email address. You can add a Facebook profile or whatever. And if your data warehouse side, your SQL side, which has a fixed schema, you could end up in trouble. So it does the data discovery, the schema discovery at the start of the operation. It looks at some data and says, I'm going to need a table that looks like this, and I'm going to create the table in Postgres and so on. It's a bit more complicated to turn that into a moving piece when the schema is being migrated. When we did this in production for my old employer, we had to formally migrate the schema on the SQL side as the schema-less CouchDB world changed. In other words, we were back in migration hell again, but only on the CouchDB, only on the data warehouse side. So yeah, if your data stays the same, you're good. If your data shape stays the same, you're good.
All right, thanks, Glenn. I apologize for audio difficulties here on my end.
That's okay.
Great. So Alan had a kind of follow-up to that, which you kind of covered, but he's asking, is that a dirty read when it's copied to Postgres?
I don't. I'm not really sure. So basically, the way I describe it is I'm turning each change into an insert or an update or a delete. And I think I'm actually doing a sort of compound query saying insert, but if it's already there, do an update. One of those queries, like if it exists sort of queries. And deletions are deletions, right? So CouchDB keeps is a bit more complicated. It keeps deletions around forever, but effectively in the data warehouse, I actually properly delete deletions. So from my experiment, it worked perfectly fine, and it was it kind of unlocks the data again. We were working blind, I found, when we had a CouchDB database on its own for data discovery tasks. It was really difficult to do that to do those in CouchDB. And when we managed to migrate the data into a SQL form, we were able to throw light on it again and discover insights into our data we didn't have before.
Thanks a lot, man. And thanks for taking the time to put this together and answer folks' questions here. This was real informative. I think it's a great reminder of just how much flexibility we have with these tools, where we're not getting locked into one particular mold, right? You have options to make it work for your particular needs.
Yeah, and we're all standing on the shoulders of open source projects, right? So my whole database journey was built on using open source tools. My employer got free licenses for open source databases, operating systems, development tools, and the stuff that we built with it was closed source, right? So that's not great. I'm glad to say that I work for an employer now that believes that you should give it back too, and that other people will build things. So I create loads of tools that I find useful, and I open source them, and some of them never see the light of day again, or no one uses them, and some people, they catch on, and I think that's great. And I encourage people to get into open source and share your work with everyone if you can, if your employer lets you.
That is excellent advice. Pay it forward, and we all build on each other's work, right?
Exactly.
Well, thanks again for your time today. If anybody has further questions or wants to see what you've been up to, you had your contact info on the top of the slide. And since this was asked, we will be making these talks available for the next year for anyone who registered for this conference. So with that out of the way, tell our engineer we're done. I have no access to chat, so hopefully you're listening.
Thanks for having me, Josh. Bye-bye.
That long?